All right, greetings. And one of these days I'll figure out how to start recording so smoothly. And our topic is metabolism. And you'll find out soon why I have that subheading. So metabolism is all the metabolic pathways happening in our body. So when we eat food, our body digests it and then breaks it down and makes energy or stores it. And then when we're still metabolizing, even when we're sleeping, because our body's repairing. And so we're always in need of energy. So it's more, well, obviously when we're exercising, so this is Joey at the highest place that we've ever been, which is like 5,800 meters. And we're looking towards China. This was during the monsoon season, which is amazing because no one's there like now. And the views were amazing because of the clouds, but this is in Nepal. And this is what the glaciers look like in the summertime. And that's what we slept on, was a pile of rocks. And you're so tired, you sleep. And I would ponder as I walk slowly all about metabolism because I'm not geeky, and that would distract my mind. And obviously it's also, so as I mentioned last year, this is when the Blazers were in the playoffs. So many of my slides, well, this is the only one because I think they lost this game then, and that was it. But when I think of jumping, also all the species, I should have a picture of my dog jumping for this. All right. So you may remember this picture from, I think, the second slide of the term. This is metabolism. This is biochemistry. This is it. That's what we're doing. You guys ready? You got your pencil sharpened? Yeah. Here in the middle somewhere is the Krebs cycle, and that's what we're going to be talking about today. And right here through the middle, right in the middle, they put glucose because it is really important. But there is much more. Over here is what's happening with all the amino acids. Over here is more amino acids. And somewhere is the fatty acids and the whole accumulation of it. And it's not just the breakdown. It is also the building up. And I apologize. I didn't mean to go that fast there. So catabolism, the next slide shows it, is the breakdown of food, and anabolism is the building up for storage. Breaking down produces energy. So that's exothermic because we're exiting energy. And the energy that we produce is ATP. So ATP is adenosine triphosphate. So in DNA, RNA, this would be an RNA molecule, it would be a monophosphate. And we're going to draw it in a moment. So this slide's a little confusing, but catabolism is the breakdown of food to energy. So food catabolism is going to change ADP, which is the diphosphate, and adiphosphate. It is the breakdown of all our food. Let's see if I can do a laser finally. Look at that. So carbs are a main source. That's what our body is meant, but also fats and proteins. And so we take a diphosphate, and that bond to a phosphate is currency. It's energy. And so we make these molecules, and then they run. ATP allows us to do work. So muscles contracting, nutrient transport, and synthesis of DNA, of proteins, of fats, because fats are our long-term storage. So anabolic is using the ATP to build to synthesize the essential compounds. All right. I call ATP the Goldilocks bond energy. So Goldilocks didn't want something too hot or too cold, just right. And so these bonds to the phosphates, and so this is what ATP, so it's showing it. I'm sorry, I keep hesitating. There we go. I'm trying to learn how to do the laser, right? After 8 weeks, you would think I would know how to do it. So this is a diphosphate, and finally he gets the third phosphate on, and he's charged and ready to go. So this, when we had just one phosphate, is what you all drew so beautifully On quiz 9, you had to draw, there's your ribose. Remember, it has the OH at number 2 and at number 3. This is adenine, and when we add it to the ribose, it becomes adenosine. And with 1 phosphate, we can build RNA molecules. With 2 phosphates, it's ADP, and then with 3, this bond is just the right amount of energy. So it's something like, I believe, 7.3 kilocalories. So I liken it to, say, carrying a $20 bill. So if you went to buy groceries, you know, a $20 bill is perfect. If you tried to pay for like yeast, I finally found yeast. We had to go up about an hour away, and we found yeast at a Safeway. But if you paid with a $1,000 bill for the $3 of yeast, they would just look at you like, that's not going to happen. And if you tried to pay with pennies, that would be 3,000 pennies. I'm pretty sure they would also look at you. That would be so inefficient. So we don't want our bonds to be too wimpy, pennies, and we don't want it to be so strong we can never build it. And then if it releases a huge amount of energy, and we'd basically blow up, right? So this is my slide, my petition that the triphosphates, all the triphosphates are important, and there are 4 of them. There is ATP, there is UTP, there is GTP, and there is CTP. So remember A, C, G, and T. Oh, wait, not TTP, because that would be DNA. So there'd be that little D in front of it. So if there's no little D in front of it, it's a ribose. But this slide, you don't need to know the slide, but it is my plug, because a lot of you do take other classes where you learn about ATP, and some of you, this is the first time you've really heard about it. So ATP is made, it is for muscle contraction, ion transport. It's really important. Oh, look at this, DNA synthesis. We use all of them. RNA synthesis, of course we use all of them. Proteins, when we make proteins, it's actually GTP. And we make our polysaccharide, when we store as glycogen, we actually use UTP. This was just a cool picture over here in the bottom right that I found. So actin, right? So when we build, we use ATP. But microtubules, which is, I think on one of these slides, it's one of our ways our body communicates with itself. And so these are GTPs. So this was kind of cool. This kind of worried me because it said catastrophe, like your communication way is falling apart, and rescue, which is GTP to the rescue. Hooray. All right, we're going to focus. Oh, I'm going to teach you about mitochondria. So here we go. Hello. We're going to draw mitochondria. And here we go. So 2 membranes. They kind of look like a peanut. You can make it any shape you want, I'm sure. So there's 2 membranes. The outer membrane, and then the inner membrane zigzags as much as you can. Just kind of have like that. And that's actually really important. So there's lots of surface area. And so we'll label outer membrane. And they are just like the cell membrane. They are, remember, the lipid bilayer. We'll be talking about that today. And then the inner membrane. Pretty easy. And in the old days when we had to remember stuff, it's really easy to remember. Kind of worry. You guys don't have to engage the memory part of your brain anymore. All right. The space in the very center, let's see if red will show up, is called the matrix. So just like all my videos are in, just like all of us live in, the matrix. So that didn't really show up. Let's try blue again. And that's, the matrix means, actually comes from the word womb, similar meaning. Maybe we'll just write it out here, matrix. And the matrix is going to be where a lot of stuff happens. There's a lot of things fluidy in there. And then there is, I'm going to put stars Stars and Stripes. It's Memorial Day. All right, and where my stars are, this is called the like an interstate highway between intermembrane space. So it's the space between the membranes. And each of these locations, something really exciting happens. So there is our mitochondria. You can have as much fun drawing it, some of you with colors. And what we're going to do now is I want to outline the 4 steps of catabolism. All right. I was hoping other colors would work. And I'm in my mermaid outfit here today. So that's why it's called a mermaid's tail. I have my mermaid tail, so that's why I keep shuffling around in my, here you can see my mermaid tail, maybe. There you go. Oh, hello. How do we go to the next one? There we go. All right, so sorry, mitochondria, that's the background of all these slides, is some groovy person's mitochondria. So this is a picture of a cell. And there's the nucleus, which is where our DNA is stored. It has its own membrane also, so extra security. Here's the endoplasmic reticulum, and it's loaded with ribosomes. And there's also ribosomes floating freely. And then these green guys, they're the mitochondria. Well, mitochondria is plural, one is a mitochondrion. These are the Golgi bodies. So Dr. Golgi, he didn't name them, somebody named them for him. These guys are the recyclers. So they recycle proteins. I mentioned that in one of them. And actually, before I do the mitochondria, these guys are so cool, the centrioles. So they have recently realized one of the things these guys do, they're the communication. So they're like, they're empty in this, they're not empty, I mean, they're a void, but they're like antennas, and they didn't really know there's all this crosswork. They thought at one point, oh, they're like an erector set, that they're creating some strength for the membrane or something, giving it its shape. And they've recently realized they're like antennas, and so they're receiving messages. And so it's something I keep referring to, that we're really, this is a really clumsy thing that I'm teaching you this whole term, which is all these biomolecules. They're really cool that we figured them out, but they're too clumsy to explain how fast we respond to signals. And so it's the centrioles. And we have the myofascia. So myo means muscles. So over our muscles, covering our whole body, is this fascia, and they believe messages move along that as electromagnetic waves, and the centrioles pick them up. In our country, we have a lot of stagnation of the signal, and that's the inflammation we feel. And that's because if you ever watch an American walk, we walk very stiff, like we're all in the military or something. If you ever go to another country and watch people walk, they're very fluid. Their whole body's moving, and at the same time, they're balancing something on their head, right? Carrying. And so I had a yoga teacher, and she was talking about that we have to really wiggle when we move. And that if we do that, that would actually help to keep our myofascia from being so tight and stuff. All right, there is a picture of the mitochondria like I drew that you should be able to draw. So the outer membrane, the inner membrane, the space is the intermembrane space. And that's where we put the stars and stripes, and we're going to see something happening there in a little bit. And the center is called the matrix, and you can see there's a lot of stuff going on there. So there's ribosomes, meaning we're making proteins. Mitochondria has to make lots of proteins, lots of enzymes. And then there's also cristae, which I forgot to draw. I draw it later on in the next part of the talk. But it's just loaded. This is just covered, completely covered. And they called them cristae because they could see these bumps with a microscope, and they're enzymes. And yes, people give the names. The thing that's really cool is this long, beautiful thing. This is DNA. Your mitochondria has its own DNA. And all The mitochondria is where ATP is made. So it's called the powerhouse of our cells. And I apologize, I didn't say that. Again, I still haven't gotten over the awkwardness of trying to put everything in the PowerPoint and not being, I have to figure out how to split the screen maybe. All right, all of your mitochondria, by the way, came from your mother. Every bit of your cell, every organelle within your cells, your Golgi bodies, your centrioles, your lysosomes, they all came from your mom, because your mom was the egg cell and your dad just gave DNA. So not actually half of your DNA, because, oh yeah, all the DNA in your mitochondria is from your mom. Yeah. Pretty cool. This kind of cool. We talk about it actually in the next slideshow. Your red blood cells actually do not have a mitochondria. And so RBC is red blood cells. Your red blood cells carry oxygen. And the purpose of oxygen is going to be the mitochondria wants the oxygen. So if your red blood cells had mitochondria, then they would keep all the oxygen for themselves and they would never deliver the load. So it'd be like if somebody gave me a bar of beautiful dark chocolate and asked me to bring it home for Joey. He said, I really want Joey to have this gift. Joey would never get it. I would probably eat it on the way home. So don't ask me to be a messenger carrying the dark chocolate. Like a red blood cell could not carry the mitochondria, because then it would use all of its own. This is actually a video. If you're interested, I can send you the clip. So we're actually a week off. So we're Memorial Day, but this was a clip a student sent me, and it is a tribute to Mom and the mitochondria that a young biology student made. And it's quite interesting and fun. And then a lot of people have fun, like in their high school biology classes and college biology classes, of having to draw cells in different ways. So you can do that also in your biology class. But ponder the centrioles. Those guys are so cool. All right, so I'm going to warn you, this is a 30-minute video because I'm going to go through the Krebs cycle and stuff. So pause me now, go take a deep breath, and I do continue after this video going through it with the slideshow. Again, I haven't figured out how to split the screen, but here we go. All right, so step one. Digest. Rest and digest. Remember, and chew your food. So digestion. So we can make it a verb or a noun, your choice. And so digestion happens in our digestive tract. And this is where we're taking our food, which is proteins, carbs, and fat. Oh, we could give them their chemical names. So instead of carbs, let's think about starch. You guys remember the name? Amylose. And fats were called triglycerides. And so we're starting with those. And what happens in digestion is they get broken down, so into their single units. So proteins get broken down into amino acids. Carbs, we should see if we can do a different color for carbs. Carbs will get broken down into glucose. And fats, they get broken down, go back to writing, remember, into fatty acids and glycerol. So most of carbohydrate and fat digestion happens in your small intestine. This is something like when you take anatomy, you can know all this detail that we know. There is a small amount of carbohydrate digestion happens in our mouth. Proteins, this is in our stomach. That's the whole pH of our stomach thing. All right, so that's the first step. And that's a step like in anatomy you get to learn a lot about when you learn about the digestive tract. Our digestive tract is really important though. We've talked about it a lot with the microbiome. And so keeping it healthy, to keep your digestion healthy, your microbiome's healthy, your emotions are healthy, your immune system's healthy. All right, so let's move on to step 2. see if I have another color. Step 2, oh, doesn't work. All right, step 2 is what the next lecture is about. So step 2 is different for each one of them. In proteins, basically though, what's going to happen in step 2 is all these different foods that we eat get broken down somehow into a 2-carbon group. You guys remember what C stands for? This is chemistry after all. It doesn't stand for chemistry, it stands for carbon. So a 2-carbon group, which is acetate. And these 3 different processes are all different and do happen in different places. They do happen, we're now in the cell, so we're now inside the cell. But somehow we have to get whatever we eat down to 2 carbons. And they all have different names. So for glucose, many of you know this is called, let's see if I can write it so you can see, glycolysis. And again, we're going to talk about this in the next lecture. I do it this way. Biochemistry books tend to do it this way. We're going to focus on steps 3 and 4 today. All right, fatty acids and glycerol go through what's called the fatty acid spiral. Sorry, not glycerol. Glycerol actually goes through glycolysis, which is interesting. But fatty acids go through a spiral. A spiral is where it keeps getting smaller or larger. In this case, it keeps getting smaller until you get down to the 2-carbon group. So you keep cutting off 2 carbons. And the amino acids go through the urea cycle. Amino acids are actually a little bit more complicated. One of the things I'll point out, and again, we're going to talk about this in the next lecture, but I want to remind you, one of the problems with proteins and this high-protein diet that our country is so infatuated with, proteins have nitrogen. This 2-carbon group has no nitrogen. This 2-carbon group is CH3 and then a COO, so it's an acetate. So that's what it looks like. So we have to get rid of that nitrogen. And that's the whole thing in the urea cycle, and why it's called the urea cycle. And that's the purpose of your kidneys. And that's why a high-protein diet pretty much destroys your kidneys, destroys your immune system, destroys everything. But hey, we probably have a drug or a treatment for that. So don't worry about it. All right, you ready? This is what we're going to look at today. The next 2 steps. Okay, we're back. I think it's going to focus on me now. You should all be focusing on me. All right, steps 3 and 4. This is what we're focusing on today. The entry into step 3 is this 2-carbon group. And the key that I want to point out to make sure you get, that 2-carbon group comes from any food you eat. That is why the past 50 years have been able to happen. That we created the crappiest diet that ever could exist. Just pure crap. You might as well start eating toilet paper. And it might come down to that. Because everybody's got a plethora of toilet paper. And you still survive. Because toilet paper is made up of carbons. And as long as you can break it down into 2-carbon groups, you're good. You're golden. Because it's all about steps 3 and 4. So no matter what you eat. I want to point this out because most of the stuff you see online focuses on carbs. Which is true. Our body is meant to use carbs. But in a time of where there aren't enough carbs, like the modern diet, you can do this through proteins and fats. But our body is meant to do it through carbohydrates. But any food you eat, so it means you can eat a food variety, any kind of food. So when the Pringles potato, whatever it's called, Pringles potato chip factory blew up one year during this term when I was teaching this, and there were no Pringles potato chips. Imagine that. You could still survive because you could get food from like real food. All right. And then the other thing, these 2 steps are called the common steps in our metabolic pathways. So they are common because they have common enzymes, which makes this very efficient. And Again, I mean, I don't think I should have to apologize. I know this isn't the best setup for learning, but hey, we're all going to do the best we can. All right, so this allows common enzymes. So once you get down to that 2-carbon group, you're good, because it's all about these 2 steps. So step 3 is Krebs cycle. There are 3 different names for this. I go by Krebs cycle because that's the guy who figured this out. And so the Krebs cycle is a cycle, it's not a spiral. And you start with a 2-carbon group plus a 4-carbon group. And you can get your calculator out, you can get your fingers out. 4 plus 2 is, oh, so that's the first step, is we make a 6-carbon group. And the 6-carbon group goes through. You're going to have to lose 2 carbons because you're going to end up at 4 carbons and another 2-carbon group comes in. But we're going to lose some CO2s. So the food you eat has to get down to this. The carbons and oxygens we breathe out, right? It's the whole purpose of breathing out. So what about the hydrogens? There's something else, though, in these molecules besides hydrogen, and it is electrons. So the other thing that happens at multiple places, 4 times in this process, so this is 8 steps, and you get 4 steps are going to be oxidation reduction. Electrons from your food are going to get transferred to these guys. So we're going to get an NADH. Maybe we should do these in red. Let's do red. We're going to get 4. So we get 4 total. 3 of them are NADH. So NADH, NADH, and we'll go through this in the slideshow too. I'm going through it now because these are things we have to write down. So we get 3 NADHs. I don't care that you memorize which steps you get it at. In fact, you don't have to memorize anything. We already went through that. And one of them is an FADH2. Again, the slideshow, we'll look at the pictures of them. And so 3 plus 1 makes 4. So we get 4 total. These guys are transporting electrons. And those electrons came from your food. Whatever food you eat, you have electrons. And that's why people can survive somehow on the crappy American diet. Because there's still electrons in the food. You're missing all the other stuff that's in the food, like the good vibrations that are in the fruits and the vegetables that Mother Nature provides, and all those phytonutrients, which are created by the good vibrations. Mother Nature really wants to help us. And oh, there's one more piece. Down here, and again, you don't need to remember what step. We also make 1 ATP. And ATP is money. So we got 1 ATP we just made. That ATP, you can use it immediately. So this is energy, yay, energy like the sun. These 4, they're going to go to step 4, which is the ETC. So we'll just write that for now. So I'm going to go up there. We're going to have to erase at some point. All right. So the big picture of the Krebs cycle, it's my mermaid waddle, is, so this is Krebs. 2 carbon from your food goes through the Krebs cycle. This is not a balanced equation. We get 3 NADHs, 1 FADH2, and these guys all go to the ETC. We're going to talk about the ETC in a moment. We also get 1 ATP. Actually, you get a GTP, and I think I already talked about triphosphates in the slideshow. They're equivalent. They're actually each used for a specific thing, but this is immediately used for energy. So you just use it. Yay. So we'll just put sun for energy. We have energy. And the other thing we make the carbons become CO2. So we get 2 CO2s, and those you breathe out. So exhale. That's the Krebs cycle. That's what the Krebs cycle does. The big points of the Krebs cycle is those guys that I circled, the NADH and the FADH2. All right, so step 4, just briefly, and then the slideshow, we'll look at it a little bit better, is called the ETC. Capital letters, because those are initials for the electron transport chain. Oh, remember what I just said? The whole purpose of your food is electrons, so you just got electrons transporting. And we'll look at that. It is always coupled with another piece, and that piece is called the OP. And OP stands for oxidative phosphorylation. So you may see me abbreviate, like when I used to be able to write on the board as I was doing my PowerPoint. It was wonderful. I had 3 boards. I could make a mess over the whole thing. All right, now I'm limited to 1 little board and a mermaid outfit. Oh, but wait till you see my eraser. All right. Oxidative phosphorylation means oxidative. Oh, losing electrons. Those guys, your food lost the electrons to them. They're going to give up their electrons here. And who gets it? The greediest of them all, well, actually the second greediest of them all, oxygen. So those electrons that came in from the NADH and FADH2, so that's the connection. That goes into electron transport, carrying electrons, and those electrons end up at oxygen, and the oxygen plus the hydrogen, we'll talk about this with the slideshow, we're going to make H2O. Again, I didn't balance it. And then you can do whatever you want with H2O. You can sweat it, you can pee it, you can move things around in your body. H2O is amazing. And so that's why it's called oxidative. It's bound to this. These two are coupled. They cannot happen, one cannot happen without the other. In fact, the Krebs cycle is also coupled, but they separated that one out. Phosphorylation means, oh, phosphate, this is where we're going to make ATPs. We're going to make a lot of ATPs. For every 2 carbon, we get 10 ATPs. And your food has a lot of carbons, so we're going to get a lot of ATPs. We used to do more fun math. Maybe I can find it for next study set. But it comes out that if you did jumping jacks, I used to make the class all stand up and do jumping jacks. Like, you guys can all pause me right now and do jumping jacks for 1 minute. All right, pause, go. All right, so you're back, and you're kind of puffing and puffing. You just burned a kilogram of ATP, or a pound. Now, it doesn't mean like burning calories. It means you took that phosphate off and went back to ADP. So that's, did I say 1 minute? Oh, you're supposed to do 2 minutes of exercise. Oh, you gotta pause me again. Go back. Do your exercise. 2 minutes. 2 minutes. I can't remember. My notes are at school, and I don't feel like going back in because it's really not fun. All right. I'm trying to remember what I want to say. All right, we're making ATP with the use of oxygen. The whole thing that's pulling this is oxygen is so freaking greedy for electrons. For those of you who've been with me for the whole year since 104, no, we only have 2 more lectures after this. It's almost over. The party's over. Right, we can sing a song. All right. That was one of the things I emphasized when I talked to you about oxidation reduction. I said it was one of the most important things. This is what drives your life. This is what drives your car. That oxygen in combustion, we're a combustion engine. We're just really elegant. We go through like 36 steps for the oxygen to get the electron from your food. The whole purpose of your food is electrons. Maybe you got nothing else from this little video clip? Electrons. And that pooling of electrons allows the phosphate to get put back on ATP, because it takes energy to put the phosphate back on, and the ATP is energy, and then you can use it to lift weights, to do whatever you need to do. All right. Oh, I have some notes myself, what I need to cover in this brief video clip, and I have a note
All right, I'm going to erase this. This is my squid hat. So here's the squid puppet, because I'm a mermaid. It's the only thing I've found that I can get to erase this wonderful board. I have tried many different things, but it works really efficiently. And I have a note. I'm going to erase these top 2 steps. They're really important. And hopefully this will be bright enough and you can see my mermaid tail. I don't want to show you it again because it's unfocused. All right. I have a note to myself to talk about feedback regulation. So oh yeah, that quiz. The quiz on enzymes. Feedback regulation is whenever you have multiple steps, and that's what all these processes are, multiple steps. So the Krebs cycle, and there's a question in your homework about this, is feedback regulation can be positive or it can be negative. So positive would be go, we're good to go, we keep going. This just keeps going in all your cells. It's going on right now. More for me right now because I'm moving around, I'm a mermaid, I can dance. You guys are all just sitting there. Hopefully you're like still doing your jumping jacks. And negative would be kind of like, oh, we can do red. A stop. It's not actually a stop. We'll say slow down, slow down. And our go should be a go, go, go. Like you're going full speed ahead. So when do you want it to go, go, go? Well, 2 situations I can think of, a couple. One would be, whoops, almost fell over in the mermaid. That would have been embarrassing. All right. When you wake up in the morning, so you wake up, your body needs ATP to get you out of bed. So you always have some ATP going because stuff is going on. Your body's repairing at night. But when you're up moving around, right, when you're exercising, so when you start exercising, we'll talk about in the next one about aerobic versus anaerobic a little bit. So that's an E. I told Joey to come in here and watch me. Even the dog Milo, I told him to come. Milo's right outside the door. All right. So if you have to run from the tiger, right, this is all gonna, we want this to go. So feedback, and when's it gonna slow down? Well, that would be at like night, the opposite, when you, at the end of exercise. So what's gonna be the things that tell you to go? Well, what's happening when you start running is you use up the ATP. When you first wake up in the morning and you yawn, you guys are doing your gratitude, so you're quietly sitting there and giving this a gentle go, but things are starting to move, you're using your brain, you're probably breathing differently than you were at night, and so you start using up the ATP. So as you get a decrease in ATP, right, you're going to get an increase. Wow, that one didn't work. You're going to get an increase in ADP, so the diphosphate, because the triphosphate's gone. So ADP increases, it goes back and binds enzyme number 1 and says, hello, wake up, let's get going. So it is a positive feedback. High levels of ADP. Another one is high levels of NAD. So high NAD is saying, I want some electrons to carry to the next step. So when you have high NAD, it means it's all, you don't, NAD and NADH, they're the same molecule, just one has extra electrons. And so once it delivers its load, it's like a Mac, I'm ready to go, like the dog's on a walk, right? I want to go. And he's ready for more. And then at night, you lay down, everything needs to slow down. So what's going to increase? Oh, you're going to get a buildup of ATP because you're not using it. And so ATP, I can't remember. You can always Google it, and you don't need to remember it. It's either step 1 or step 3 the ATP binds to that enzyme and pretty much says, let's go to sleep now. High NADH. So again, NADH and NAD, same molecule. NADH has the electrons, but you're not breathing in the oxygen like you were when you were exercising. You've slowed down. So there's not as much oxygen needing electrons. And so the NADH is building up. It's a supply and demand. So when the supply increases, because the demand is down, it's kind of like the toilet paper thing. All right. So one more thing I wanted to do, which is the math. Please ask questions. This has been the hardest thing for me. I'm going to ask you guys for feedback, but the hardest thing for me is this asynchronization, because my other class, we're doing live lectures. Not everybody's there, but there's 3 to 5 people, and they ask questions, and everybody else is telling me, oh, I'm so grateful for their questions, because I know you guys have questions. So at least ask in office hours. This is metabolism. This is why doctors bow to me when I used to go to a doctor. Like, oh my gosh, you're a biochemist. Because of metabolism. And it's not hard. So we're going to do the math starting with a 2-carbon group. So if you have a 2-carbon group, so we'll go back over this, is you get 3 NADHs from the Krebs cycle, 1 FADH2, 2 CO2s, that those go away. So they have nothing to do with the math. And you get, oh, that one, it's actually GTP. I'm going to write it correctly. But that 1 GTP is equivalent to 1 ATP. All right. Need my squid hat to erase to give me more room. All right. And the NADH, once it goes through electron transport chain, it is equivalent, it has the ability, each NADH, to produce around 2.5 ATPs. It has to do with the potential energy. So 3 times 2.5 has the potential to make, and this is like a serious roughly, 7.5 ATPs. Now, quick disclaimer, I no longer have you do the math. There's one question in the homework, just so you get an appreciation for it, but I never ask them on tests anymore because a lot of books have different numbers. And it is because this was all done in a test tube, and when they started doing it for real, they realized they overestimated the numbers. FADH2, and we'll look at that when we look at it on the slide, has the potential of only 1.5 ATPs. So that 1 FADH2 is 1.5 plus 7.5 is 9 plus 1, and we get 10 ATPs for every 2-carbon group in your food. But your food is made up of more than just 2 carbons. It's made up of a lot of carbons. So in the next slideshow, which will be for next week, we're going to go back and we're going to see how many 2-carbon groups we can get. And that's where the numbers get crazy huge, like in the hundreds, for every 1 fatty acid. And you're going to have gazillions fatty acids, right, when you eat your French fries or whatever. So you have all this potential for ATPs that you could make. Again, it's potential that you could have. Your body has to use the food. So that's the whole thing with exercise. Not saying you have to go run a marathon, but moving around. Go plant a garden. All right. That's our mitochondria. Every cell has lots of mitochondria. The Krebs cycle, I forgot to mention where these last 2 steps happen. So it's good. I can erase that. And we're almost done. These 2 steps happen in the mitochondria. Krebs cycle is in the matrix of the mitochondria. So those 8 steps are 8 enzymes, and they are in the matrix. Actually, I lied. 7 of the 8 are in the matrix. 1 is actually stuck on the membrane for some reason. So that's in the matrix, in the womb, inside. I had somebody one year who made that into a beautiful cradle. And the ETC is happening in the rest of the mitochondria. So oxidative phosphorylation is the inner membrane. So usually, I knew I left something out. The inner membrane is folded. Remember we talked about the folds, and then I forgot why I folded it. I forgot to explain why I folded it. I didn't forget why. It's just lined with enzymes, and it's the enzymes for this step. All right. So, I need the squid hat. Oxidative phosphorylation happens on the inner membrane. That's where all of its enzymes are. The ATP is being made in the matrix. The ETC is also the inner membrane. So both of these are the inner membrane. Where I put those stars, the space in between, that actually is really important too. So I guess the ETC we can say is the inner membrane and also the space. That space is going to be really important. The outer membrane is just the package that's holding it all together. So again, the thought is, and then these are in our cells, that a cell ate another cell, which would be this one got eaten, and it was really good at making ATP. And the big cell that ate the little cell said, wow, this guy's really good at making energy. And it all went from there. Okay, so many blessings. I don't know how mermaid does blessings, and I'll see you soon.
All right. So, if you're still with me, this is what I just went through. And please don't try and write all this down. It's actually in your book. So I have to make my little pointer again. These are the first two steps, which the next slideshow, study set 12, is about. We're starting here today with acetyl acetyl group, the 2-carbon group. And we're going to go through what I call the Krebs cycle. It has a couple names, and electron transport. So these are the 4 stages. And yeah, I don't really like his words as much, but you can pause and look at it. So the citric acid cycle is we're losing the carbons and the oxygens that were in our food. And what moves on to that last step is that NADH and FADH2 are carrying electrons, and this is where the ATP is going to be made. Oxygen is here at that last step. And let's just move on. All right, so I call it the Krebs cycle. It is also called the citric acid cycle, or CAC. One of the biology teachers here calls it the CAC. Which I've never heard anywhere else, but just an abbreviation. And that is because the very first step you make citric acid. Oh, but you don't. Because there are no acids in our body, it turns out. They're always ionized. The true name that Dr. Krebs called it was the tricarboxylic acid cycle, which is the TCA cycle. So when I look in my biochem book from when I was in college, that's what it's called. And that's because here, citrate, so over here, let's see if I can get a laser pointer again. Oops, let's go back. This guy's a little obnoxious. Anyway, it was called citric acid cycle because the 2-carbon group combines with a 4-carbon group and makes citrate is the correct name. The hydrogens are no longer there, and so it's 3 carboxylic acids. For those who took Chem 105, this step number 2 is actually really cool. This OH here is a tertiary alcohol. Remember, primary, secondary, and tertiary alcohols? And tertiary alcohols cannot be oxidized. And that's actually what this whole cycle is about. So this first step, we put it together. And the second step is we change a tertiary into a secondary alcohol. All right, you don't need to know that. Yeah, I had to cut a lot of stuff out that I can't do. All right, these, you can see there's a whole bunch of steps where we make these lovely purple molecules. And we also make a GTP. Isn't this wonderful? They show it correctly. All right. And he won a Nobel Prize. And I love that picture of him. So this is just a GIF. It's a little annoying, but it is showing you, I haven't figured out what the orange and the blue balls are, but that the carbons that are from your food eventually become CO2. And right, we'll just move on. This was a little, let's see if it's going to play. There you go. It's a little 44-second YouTube.
In the citric acid cycle, a 2-carbon compound reacts with a 4-carbon compound to produce the 6-carbon compound citric acid. In subsequent reactions, 2 carbons are lost to CO2, electrons are stored, and ATP is produced. By the end of the cycle, a 4-carbon compound remains, ready to react with another 2-carbon molecule and begin the cycle again.
All right. Let's see where we go next. So a couple things to point out from this that is coenzyme A, or a lot of places I always learned it as just CoA. CoA is what carries that 2-carbon group. That 2-carbon group comes from any food you eat. And this is coenzyme A. This is really cool. You don't need to know the molecule. You just need to know what is up there in the green and hot pink. So this is an ADP with an extra phosphate. And then it's hooked up. This is one of the B vitamins. So if you've ever heard you should take B vitamins when you have low energy or you're stressed, has to do with the Krebs cycle, because they show up in the Krebs cycle in a lot of places. And then it's hooked to something. And then the sulfur is what hooks up to the 2-carbon group. And it transports the 2-carbon group into the Krebs cycle. And all right, let's see. And I just asked again, so 2-carbon group is also called an acetate or an acetyl group, acetyl group, and it comes from any food. So healthy food or crap food. All right. These guys are the key. These are the connection between the Krebs cycle, which we just talked about. Yes, we're going to move on to the next step. These guys transport electrons between the Krebs cycle to the ETC. They are the couple, the coupling step. So just again, looking at them, they do have a full name. You do not need to know it. So you don't have to worry about writing that down. Some of you probably stopped me and already wrote down lots of notes. That's what Joey does. There, look at this again. We see an ADP, and then we hook stuff on. And nicotinamide is vitamin B3, and riboflavin is vitamin B2, hooked up to another ADP. Isn't that crazy? These ADPs just keep showing up everywhere. But the whole thing, and these guys will make a bond to a hydrogen. These guys are all about, that's a red ox, because it's oxidation reduction. And so that's why I say what type of reaction. So remember, Leo is losing electrons and hydrogen. So rather than looking at the electrons, we're going to be looking at hydrogen. So right now in the Krebs cycle, these guys picked up hydrogen. So they picked up the electron they gained. So they are now in their reduced state. So in the Krebs cycle, they're going through reduction. And yeah, that's just saying they were the B vitamins. Just kind of a cool fact. I think I asked what vitamin. So it's not vitamin C, it's not vitamin E, it's not vitamin G. There is a vitamin G. It stands for going outside and standing in your bare feet on Mother Gaia. All right. So I talked about this in my little video, and then I found this cool picture. So feedback regulation, there is positive and negative. Most people talk about the negative feedback. And in the Krebs cycle, that would be anything that was a product of the Krebs cycle. The NADH especially can go back here and it can block step 1 and step 4, it looks like. No, it's step 3. So, and ATP also will block at step 1 and step 3 somewhere because it's a product. And again, this correctly shows it does come off as GTP, which we consider equivalent. It can trade its phosphate to the ATP. So when would they accumulate? When would you get high levels of ATP and NADH that they would suddenly say, hey, let's slow down, let's slow down? Well, when you're at rest. when you're not using it. So while you guys were watching my video, I went outside and meditated, and all the animals came out and slept in the sunroom. And that's what they're doing right now around us. They're all in their little pillows. They just like to stay around me. I'm like Snow White. I don't have a Snow White outfit, unfortunately. All right. Positive feedback. Probably because I don't need one because I'm already her. Positive feedback would be ADP. So that's the green goes here. Go, go, go. And calcium also, but well, ADP. So ATP is being used up, so we need more. So that would be when you start exercising, moving around. Today, if you get up and do your jumping jacks, you can do them at any time. That's the thing that's so beautiful about this way of learning. You can stop me at any time and then come back. All right. And also when you wake up in the morning, your ADP, you're going to start using up the ATP, and you'll need to make more. All right. So, see if you've been listening. How are the two coupled? Well, the Krebs cycle and the ETC are coupled. Oh, by these. I don't know why he illustrated them like this, but the NADH and the FADH2, the electron, the little molecules, they're called coenzymes. Remember we learned about coenzymes? Right, so it's showing the citric acid cycle. Again, the Krebs cycle occurs inside the very center of the mitochondria. We're now in a cell membrane here, and so this is that inner membrane. So these guys are inside the very center, and then they're right there, and they just go boom, right to these complexes. So the ETC, and I think on the next slide I wrote out in words, is electrons transport chain. In case you've never heard of it, ETC is just a lot easier to say and also to type for me. So electron transport chain, it historically was actually called the respiratory chain because it involves oxygen, and I keep forgetting to get my pointer to work. Actually, sorry, I want to go back one and talk about it. So what is happening in the ETC, the NADH and the FADH2, so down here, they give up their electrons. These big purple blobs are complexes. They're protein complexes. And the electrons, this blue arrow, these are electrons, and they're being passed between these complexes. These little ones, the CoQ and the cytochrome C, they are they're floating back and forth between. These other ones are embedded. So this is CoQ10 that a lot of people take when they have heart health weakness, and this is why, because it helps us to make more ATP. FADH2 is a little bit greedier. So what's happening with these four complexes is complex 4. When I do this in class, where you guys are all sitting in a row, and so we'll say Joey comes in and delivers his electrons. He's NADH, and he gives them to John. And John gives them to Shayla. And Shayla passes them on because Dominique's greedy, and Dominique wants them more. And somebody else comes along. And then here's Olivia, Dominique's daughter. And she's like, no, I want them. They're mine. And she grabs them all up. Oh, but wait, don't get too greedy, Olivia, because the greediest one of them all is in your breath, and it's why you breathe. Oxygen wants those electrons. But as opposed to your car, which does this in one step, and you have combustion, our combustion was those 36 steps starting from our food. And so these electrons, this passing of electrons from one complex to the next, why doesn't it go straight to oxygen? This is a potential energy change, and that change in potential energy creates energy to do another step. So there's 2 steps to the ETC. So one is this flow of electrons between complexes from NADH and FADH2 to the oxygen. In my calculation, remember my little math thing, FADH2 did not have as much potential because FADH2 was greedier and it held on to its electrons. So complex 1 can't grab them from it. This was John. John doesn't have enough strength to take these electrons. So he's like, oh, well, there's a lot more NADHs anyway. All right. So this is just a picture. So those little E's, these are those GIFs people can make, and these are pretty cool. And I know, right? Look at them sliding along. It's like an amusement park. And I guess there's words at the bottom telling you what's going on. In the center, mitochondrial matrix. And this would be from FADH2. And these would be from NADH. All right. There's going to be another step, and this is the second step. So you can stop and write this down. ETC is a proton pump. A proton is a hydrogen ion. So if you remember, hopefully your Chemistry 104 teacher taught you when you have a positive charge, you lose an electron. Hydrogen was element number 1, so it only ever had 1 electron. So if it loses that electron, it becomes an H positive. Now it has no electrons, and it is just a proton. All right. So ETC is a proton pump. 2 steps to the ETC. Electrons are passed between complexes. That creates the potential energy. That potential energy is used to pump protons across the membrane. So here's the hydrogens. Oh, and you should have also learned in Chem 104, whenever you have a lot of hydrogens, or when we talked about proteins, lots of hydrogens means you're acidic. The intermembrane space is extremely acidic. The matrix would be basic compared to it. So this is that full GIF. So the electrons are moving along, and as they do, so pumping, if any of you have ever pumped water, it takes energy. And so the energy to create a gradient always requires energy. All the other gradients in your body, the energy to create the gradient comes from ATP. But we're trying to make ATP, so we can't use ATP. So this is brilliant. This is simply brilliant. So a hydrogen gradient is made. To make the hydrogen gradient, you use the electrons that came from where? They came from your food. All right, we're not done. There's still one more step. Let's go. This is just me being geeky because I love proteins and they're so beautiful. So there's the complexes. They are complex. They are made up of, remember that quaternary structure? Maybe, maybe not. Maybe you want to forget it. These guys are really complex. They have quaternary structure. They are in the little mitochondria. And then you have lots of mitochondria in every cell. And we'll talk about more in the next slideshow. But more mitochondria isn't actually better. It usually means earlier death. So you don't want too few. It's the Goldilocks thing again. All right. So we have one more step. So the ETC, electrons flowing, creates hydrogens. We have one more step, which is here. Complex 5 is what they're calling it. And yes, this is in another language. So if you're going, it's blurry. It's because it's in another language. So you won't be able to read it anyway. All right. And what that last complex was here, this beautiful thing, this is how they illustrate it. It is called ATP synthase. It's an enzyme that synthesizes ATP. See if I can get my pointer back. I'm so not good at this game. All right. The only place the hydrogens can flow down the gradient back into the matrix, because gradients, it's the whole idea like a dam. The inner mitochondrial membrane is a dam. So the hydrogens pumped out, and now they want to come back in. So they're getting pump, pump, pump to create the gradient, and they want to come back in. And the only place they can come back in is through this enzyme. It's a channel in a turbine. So the hydrogen turns the turbine, and this is like a picture of it. It is so cool. It's like this little amusement park ride. There are millions of ATP synthases. Those were the cristae that are just coating your mitochondria membrane. And so as it comes in, so you know, like when you walk, if you went to the zoo when the zoo used to be open, gosh, to be a zookeeper now would be awesome because there's no people around. You just get to be with the animals. Anyway, so the hydrogen goes on and it turns the turbine, creates mechanical energy. That mechanical energy actually twist the adenosine diphosphate, and then there, I don't know if anybody's noticed, but it keeps saying P with a little I, and that P with a little I means inorganic phosphate. It means it's just a phosphate, and it puts them together, and now you have ATP. And it is insanely cool, like this guy who made this GIF. This is so cool. There's really, somebody asked me, do you have recommendations? Oh my gosh, I Googled Krebs cycle, and there's a zillion, really, a zillion people who've made YouTube, and you each are gonna have a preference. So if you feel a need, you can go find one that works for you. So this is just showing it all together. The electrons came from your food, the NADH, the electrons in the Krebs cycle got transferred to NADH. NADH becomes NAD, gives up its electrons, the yellow flow. Those electrons moving creates a hydrogen gradient. Hydrogen comes back in, and boom, we got ATP, energy. And now that energy, that ATP molecule is like a $20 bill or a $5 bill or a $7.3 bill. All right, so that step of making the ATP, this step, I don't think I gave it a name, I did on the board, is called oxidative phosphorylation. Oxidative phosphorylation is OP. There are two ways to make ATP, and I just realized. So this is the Krebs cycle. That is called substrate level phosphorylation. So that is the Krebs cycle. Anytime you make ATP, not using the ETC, it's substrate level phos. That's misspelled. You can write that in my evaluation. She doesn't know how to spell. All right. Oxidative phosphorylation means oxygen was involved. Remember, it was a greedy one. It was the last step in the ETC. And so the last step in the ETC is why this involves oxygen, or really what it's from is the electrons, because oxidation means losing electrons. And so that food is losing electrons. And right. So two ways to make ATP. The vast majority, over 90% of your ATP, might be like 95%, is made by the top one there, oxidative phosphorylation. That's why we just went through it. But if you remember, when we did the math, there was one that came from the Krebs cycle, 1 ATP, but the other 9 out of our 10 came from oxidative phosphorylation. All right. So these are just some cool things. Cyanide poisoning. It's actually got to be, it's really sadistic. Cyanide binds to that last complex. Remember complex 4 in the ETC? Cyanide binds to it. So basically your body breaks down your food, goes down to the 2-carbon, goes into the Krebs cycle. The electrons get transferred. You're breathing out CO2. And those electrons go and they get stuck at the 4th complex. And oxygen cannot get its electrons. So you can physically breathe in oxygen. Oxygen can move to your cells. Oxygen can't get its electron. And you suffocate. There's no pillow over your head. You can breathe perfectly fine. But since electrons cannot get to oxygen, you turn blue and you're dead in a couple minutes. All right. And then there's this guy, therminogen, is what hibernating, they give birth during hibernation. They lose like half of their weight or something crazy. But hibernating bears they don't need a lot of energy, but they still need to stay warm because they're usually in really cold places. So it turns out brown fat has protein channels in the mitochondria that allows the hydrogens to come in without going through ATP synthesis. So they basically go through all the step without making lots of ATP, because the ATP, remember, stopped everything from happening. So it's a way that the body can get around making ATP. It only happens while they're in hibernation. It's pretty cool. All right, the last thing we're going to talk about is free radicals. And we've talked about them a lot. And maybe you may have not noticed when we did this, when we talked about sugars, when we talked about fats, when we talked about DNA, I don't know if anybody ever noticed, there was a mitochondria in the picture. So we know UV light, right? That's overrated. Ionizing radiation. Smoking, right? They banned it in 1964 and smoking went way down. Air pollution, it's gone down. We should all be healthier. Oh, inflammation, because you eat crap. Don't eat toilet paper. I should have put that disclaimer from before. Don't eat your toilet paper. Don't. Your mitochondria creates free radicals. We're going to go through it on the next slide. Those free radicals can cause DNA damage. These are all those sources we talked about. Oh, I forgot to ever mention air pollution. Oh, but we're cleaning it up. That would be wonderful. Oh, and you guys don't smoke? Tell me you don't smoke. And you don't drink soda. You definitely don't wear it as curlers. Oh, and that virus? Bye-bye, virus. Bye-bye. None of you eat. Please tell me you're not on the low-carb, high-bacon diet. You might as well, if you're doing that, just go down to Hanford and start licking the plutonium that's there. X-rays, well, dentist offices have been closed, so don't have to worry about that. Okay, special occasions, desserts are a must, but learn how to make them healthy. You can. So bye-bye. Healthy desserts are awesome. Oh, this can be your next extra credit. You can watch Super Size Me, even if you've seen it before. And then there's a new one out that I haven't seen, and he owns a fast food joint or something. Yeah, we talked about You Are What You Eat, talk about more. Oh, stress. Stress is a big cause of free radicals. Let's get rid of stress, because we don't have to go to school anymore. Maybe never. Okay, the sun is up there because the sun, yeah, the whole UV thing. But again, if you don't get sunshine, you also cause damage. So it's the Goldilocks. The Goldilocks. You all know you feel better when you stand in the sun and smile. So absorb, make some vitamin D. Nobody has yet picked vitamin D as a topic. I can't believe it. There's so much in the news. All right. There's a reason this was the background when I did that slide. This is air. It's not dandelions. It's not that you have hay fever. This can cause free radicals or the ladybug. It is the air you breathe. It's one of the biggest sources. And it's not the air pollution that was gone because none of us are doing anything. And that is because these guys, ROS. All right, radical oxygen species, because they're free radicals. They come from oxygen. And Rho just didn't sound as cool as ROS. These are them. OH. It is not OH negative. It is not hydroxide. It is OH. It ends up with only 7 electrons. Oh dear, we have an odd number of electrons. So that last step in the ETC is the oxygen coming together with hydrogens and making water. And sometimes it just doesn't get together correctly. And it comes together like this, and you have only 7 electrons, and oh my, it needs another electron. And it steals it from your DNA, from your cell membranes. Right, number 2, hydrogen peroxide. This is why dentists and dental hygienists love hydrogen peroxide, because the oxygen here is in a -1 oxidation state, and oxygen likes to be -2. And so it's missing an electron. It wants to be H2O. H2O is the perfect molecule. It doesn't want to be H2O2. So it is desperate to find another electron of its very own and move out. And so it steals it from bacteria, and your teeth become whiter. And number 3, there's others, but these are the 3 big ones. Oh, this doesn't make sense at all. It's an O2 with a -1. Yeah, it's an oxygen that got greedy. It got a negative, but it didn't get a hydrogen. And this guy is called superoxide. When I was in graduate school, many, many decades ago, most of you were not born yet, one of my teachers was Dr. Friedovich, and he was Dr. Superoxide dismutase. So we actually have an enzyme in our body that mops up this guy, because this happens. This happens a lot. These guys are 3 big free radicals. They actually help to keep our body healthy also. But this is ROS, this is this is a mitochondria. Let's see if I can get my laser. There's our mitochondria. It's producing these guys. And then they go in and cause damage, and you get cancer, and then you're dead. Or it just keeps propagating itself, and you get more cancer, and you feel like crap, and you're dead. Or you get DNA damage, right? The ROS just goes right to DNA damage, and you're dead. Oh, or it stresses the ER, right? Yeah. All right, let's move on. Oh, so as you get old, this is just, it's going to happen more and more. The machinery is getting older. Oh, does it have to happen? That is the question. For those of you who are really into the Bible, no, they lived 900 years, right? And then I was very amused because I asked that question, what is the half-life of DNA? And I didn't realize until some people emailed me, and then all of you said the same thing. I just Googled it, which is what I would have told you to do. And when you Googled it, Google said the half-life of DNA, basically your DNA lasts as long as you do, right? Is 521 years. So does that mean our DNA should be making it 1,000 years? Should we be living 1,000 years? I know you're all horrified going, what? All right. Anyway, imagine making 1,000 years, but not like this. Well, with a very healthy brain. Where's my next one? Oh, and just breathing. This is the power of meditation, as you slow down your breathing. So you're getting less oxidative damage. You're also slowing down the stress. Breathing through your nose is better. There's so much stuff out there now about that, but breathing through your nose, you're breathing less oxygen than a big gulp through your mouth. So that's the whole thing about extend your life. By breathing through your nose instead of panting like a dog. It slows down your heart rate, so it slows down ROS. Oh, wait, this is like the bad things that happen. So these are all the cancer symbols. Yeah, purple is prostate, in case you didn't know. Everybody knows pink, but they don't know all the other ones. Teal is the other female, so ovarian. They put all the other ones like in one. All right, this is your cell membranes. Big deal. It is. That destroys your cells. That is cell death. That's not good. And I'm pretty sure it's hydroxyl radical. That is, so remember this is happening in your mitochondria, and you got two membranes there. And those membranes are really important. And you're making these free radicals in there, and they're going to start destroying those membranes. Hydroxyl loves cell membranes. It loves to destroy them. And then your mitochondria is no good. And then you have no energy. And then it's, yeah, not a good thing. All right, we talked about damages the heart, damages the liver, damages your eyes. Yeah, why would you do that? Damages your skin. Oh, big topic right now that is driving me crazy. Why has there been nothing about the long lines at all the fast food places? Why is everybody going out for fast food? Why are people still smoking? They're telling us wear a face mask, and then people are smoking. So maybe they should consider banning some other things too to make people healthier. So lots of inflammation, that's a cancer cell. Yeah, it really wants to be normal. It wants to be normal. And so, yeah. All right, so free radicals over here on the left. And if you're going to keep eating that, you're going to keep getting more and more ROS. And we do have antioxidants in our body, and from the food we eat, and from our attitude. You have a choice. Not to sleep on your choice, but if you don't get enough sleep, you're also going to have a lot more free radicals. People who say, oh, I'm fine with 5 hours of sleep. I'm perfectly fine. You're not. And you're not getting 5 hours of sleep. That might happen once or twice. And at night, melatonin is the most powerful antioxidant. Doesn't work the same when you take it as a pill. You need a face mask. Turn off all electronics. Start getting real sleep. Start allowing your body to repair. Go have a picnic. Dress up and have fun. Go buy yourself a mermaid outfit. Somebody bought me that. So the dress, I was wearing the pink dress, was actually a Charleston, do the Charleston. It was a dance from the 20s, from the great before the Great Depression, I don't know. And when I was 10, my mom made me that outfit because I was in Girl Scouts. And yes, it still fits me. And so that's what the pink one, then somebody bought me the mermaid tail, and I didn't know what it was. And then finally, a student explained, I brought it to class, and I'm like, what is this? And they're like, you're supposed to wear it. And I didn't understand how, but it is that you can't move around when you're in it. All right. And it's meant for children. I'm on the smaller side. Go for a bike ride and have fun. Learn to be silly. Learn to laugh. Oh my gosh, last night I was out meditating, and my neighbor, I don't know, maybe she could see me. I don't really care, but I know they can't. But she must have been on a phone call with somebody, and she just started laughing, and she had like the best laugh I've ever heard. And then I realized I don't know any of your laughs, because in this setup, I don't get to hear laughter from any of you. This is one of your lab, I don't even know what lab we're on. Lab 8 is telomeres. And I'm going to wait and see if anybody picks the giggle until you jiggle and wiggle. This little boy is jiggling and wiggling, and he's getting the little boys around him to jiggle and wiggle too. I'm really hopeful somebody picks that one. You got to do it every day and get somebody else to jiggle and wiggle with you. Can you imagine what joy, not just in your life, but everyone's life, to do that? All right. And yeah, be playful. That was doing yoga. I can't stand on my hands like that, but neither could that dog. All right, this is ORAC, O-R-A-C, which over here it tells us. Sorry, I couldn't remember what it meant. So ORAC is oxygen radical absorbance capacity. Whew, that's a mouthful. Probably all stopped me, wrote it down, and oh, look, we can read what it is, or you can just Google it. Basically, it's how good are these guys at mopping up all those free radicals? Because, come on, we got to breathe, right? Right now, in these bodies, that's what these bodies do, is they breathe. So when we all make that transition to the next level, that's right. If you listen to all the new age things, that's what's going on. And then we won't have to worry about this. But right now, we're still here. So these are some of your top ones. And oh my goodness, is bacon on there? Don't think so. Wow, what is that one? I don't even. Next to, that's noni. I think I had students who were from the Philippines last year, and they had to explain pomegranate. These guys are amazing. Does it matter which one? No. Eat which ones you like and eat a variety. Eat the skin. My mom used to have to peel grapes for us when we were little kids. Anyway, make smoothies. It doesn't matter which. If you don't like it, don't eat it. These guys are so astronomically expensive. They didn't used to be. And then somebody said, oh, they have a high ORAC. And people don't know, but they go back and they fill in the missing electrons. So see, this guy's a free radical. Oh, no. And then they fill it in, and everything's better. Oh, have you picked a topic yet, by the way? Pomegranates? All these things. Strawberries are taken. It's going to be strawberry season. This is usually when the people who don't have a topic suddenly come up to me at the end of this lecture and say, does anybody have this? Does anybody have that? Nobody has chocolate. Chocolate shows up on this like 3 or 4 times. So the fruit is down here in this part. Look at these numbers. Look how high these numbers are. So the goji berries was 25,000. We're getting up to 300,000. These are your spices. You've got to spice up your life. Cinnamon, oregano. Nobody's ever done oregano. That would be an awesome topic. Spice up your life. Basil, chocolate. 3 times chocolate showing up there. All right. This was really cool. So they used to tell you when you had cancer, you got to stay home and rest. You got to stay home and rest. Now they tell you got to go for a walk every day. And so this was a quick Google. That's why it's straight from, don't do this in your talk, put it in your words. But I have this because I wanted to talk about your talks briefly. Make Make sure you have references in your paper. It's up to you if you have it in your talk. But this is because it was James Watson and others proposed a lack of ROS due to a lack of physical exercise may contribute to the progression of cancer. So if you remember a couple slides ago, I said, it turns out ROS, there's a Goldilocks level, and it's actually a protection. It's killing the bad guys. Too much, it kills us. Too little, bad guys win. And so spikes of ROS are needed to correctly fold proteins. And yeah, all that good stuff. So low ROS may hamper the formation of tumor suppressor proteins. So exercise, not over-exercise, over-exercise too much. Exercise induces a temporary ROS spike. Exercise is very beneficial. This is 12 years ago, and this has been much more, like now we know about irisin and other stuff, but it's the ROS is a big factor here. Anyway, and the biggest factor with ROS, turns out, is gratitude, which is your lab. It lengthens your telomeres, does an epigenetic shift, and keeps your ROS at just the right level. Oh, I didn't realize. Yeah, you guys, you pick one of those categories and you have to do everything within the category. And I forgot to tell you folks, everyone should be saying grace no matter what category. So if you're doing the G-bombs, when you make your G-bomb salad, say a prayer over it. These little kids, look at that. And if you're saying gratitude to someone, also say grace. And if you're giggling and jiggling, you can make a grace that makes you giggle and jiggle, but then, yeah. And I don't remember, oh, service. Always say gratitude. Always kiss the cook. Say